Okay, so let's take a look at some practice problems that cover what we did in this entire module. Number 1, determine whether the outcome is a type 1 error, a type 2 error, or a correct decision. So a test is made where the null is that the mean is equal to 63 versus the alternate where the mean is greater than 63. The true value of the mean is 75. Now if that's true, if the true value of the mean is 75, then shouldn't we have been rejecting the null? We should have been, but it says the null was not rejected. So if you do not reject in error, so if you don't reject when you should be, then this is exactly what we would call a type 2 error. And we call it a type 2 error because remember, there's I think of it as being 2 words associated with this. So if you don't reject the null hypothesis, but you should be, that's a type 2. And we can contrast this with a type 1 error would be where you reject the null when you shouldn't be. Okay, number 2, height and age. Are older men shorter than younger men? According to the National Health Statistics reports, the mean height for U.S. men is 69.4. In a sample of 300 men between the ages of 60 and 69, the sample mean is 69.0. Public health officials want to determine whether the mean height mu for older men is less than the mean height of all adult men. And so our hypotheses can be set up, and we see that we are focused on means here. We're talking about mean heights. And this very last statement really embodies what our alternate hypothesis is going to be. It says the officials want to determine whether the mean height mu is less for older men than it is for all adult men. And so my alternate hypothesis is going to be that the mean height of older men is going to be less than 69.4 because 69.4 is the mean height for all adult men. And if this is my alternate hypothesis, then the null hypothesis is that the mean is equal to 69.4, that there is no change from, there's no change between the mean heights of older men and the established mean height of all adult men. Part B, let's assume the population standard deviation to be sigma is equal to 2.84. Compute the value of the test statistic. So when you're doing a hypothesis test and it involves means and you're given sigma is equal to 2.84, this is a z-test problem. And the other thing is it's not mentioned in this question, but the sample size, remember, needed to be sufficiently large, and I think it was. I think we had a sample of 300. So let's go to z-test and plug in our stats and see if we can get a test statistic, see if we can get a p-value, and then state a conclusion. So I'm going to change this to stats. And the null value of the mean is 69.4. Sigma is assumed to be 2.84, so we can enter that in. X bar is 69.0. And our sample size was 300. Notice the alternate hypothesis is less than, so I do want to select the less than symbol. And then I can go calculate. My test statistic is z, so my test statistic is z is equal to negative 2.4395. So in other words, my data of 69.0 is, it's almost 2.5 standard deviations below the mean if we assume this to be our mean. And so that's pretty dramatic result in our sample, so it's not a big surprise that you would see a p-value be this low, where we see p is equal to 0.0074, and even at a low significance threshold of 0.01, that p-value is less than 0.01, implying that we can reject our null, and if we are rejecting the null in this case, then we are accepting that the average height for older men is in fact less than the mean height of all adult men. So we can say that older men are in fact shorter on average. Okay, let's scroll down to another example. And in this one, this says, is there a doctor in the house? The Bureau of Labor Statistics reported that in May of 2009, the mean annual earnings of all family practitioners in the U.S. was $168,550. A random sample of 55 family practitioners in Missouri that month had mean earnings of $154,590, with a standard deviation of $42,750. Do the data provide sufficient evidence to conclude that the mean salary for family practitioners in Missouri is less than the national average? Okay, so this is going to be a hypothesis test. It's not completely evident maybe at first, but as you glance through the problem, you see that they're asking us for hypotheses. They're kind of just breaking it down for us, and then they give us that significance level at the very end. So we're going to set up some hypotheses, and we have to decide, is this going to be a hypothesis test involving means or proportions? But look for the key words in here, especially at that last statement, that last question, again, a lot of time reveals exactly what we're working with. And it says, do the data provide sufficient evidence to conclude the mean salaries? That's what we're talking about as a mean here. And so there's going to be mean is equal to some number here. And in the alternate hypothesis, we are saying is the mean less than a certain number. So think about what number goes here. The number that goes here is going to be the same in both spots. And it's, a lot of times I think of the null value, or what's the value if there is no change, between the salaries of these Missouri doctors with the salaries of doctors around the entire country. And if there's no change, then you'd say, oh, well, the average is going to be around this 168,550, because that's what the national average is. But we're hypothesizing, no, we're, based upon our sample, we're thinking, it might be a little bit lower. So we're hypothesizing that the average salary of these Missouri doctors is in fact going to be less than 168,550. You should know that the only difference between the null and the alternate all the time is just the symbol in the middle. Okay, compute the value of the t statistic. How many degrees of freedom are there? So the reason it's saying compute the value of the t statistic is when they give you the stats in this problem, including the standard deviation, the stats that they give you are relevant to a sample. And if we're doing a hypothesis test involving means, but we only have a sample standard deviation, and so I'm going to label this S is equal to 42,750, then that means our test statistic is going to follow a t-distribution. That means the test that we need to use in the calculator is t-test. So I'm going to go to t-test in the calculator, and I'm going to see how far this sample mean, how many t-scores, in a sense, that sample mean is from the assumed population mean of 168,550. So here we go. We say stat, test, t-test number 2. The null value of the mean is 168,550. Our sample mean, that's where we enter the 154,590. S, the sample standard deviation that's been provided, is 42,750. And you should know, if you typically do not see the sigma symbol in the problem, we don't see it here, then you're most likely going to be using t-test. Okay, and our sample size is 55. And so that is sufficiently large, it's greater than 30. So we calculate, and we can see that our test statistic t is negative 2.4218 if I'm going to 4 decimal places. And so that means that our point estimate of 154,590, it's almost 2.5 standard deviations below an assumed mean of 168,550. In other words, it's pretty unlikely to get something that's that far away from the mean unless maybe your true population mean isn't this. And that's exactly what's confirmed in our p-value right here. As you look at the p-value, we could see that p is equal to 0.0094, and 0.0094 is less than 0.05. And so we will reject the null. And when we reject the null, at the same time we are accepting that the average salary for the population of family practitioners in Missouri is less than $168,550. So our conclusion is Missouri doctors make less. Missouri docs make less. I realized as I was finishing this out, I forgot to mention how many degrees of freedom there were in this problem. And remember, when we talk about degrees of freedom, it's just a simple formula. And it's related to our sample size. And so the number of degrees of freedom in our problem is our sample size, which was 55. So we're just going to say 55 minus 1. So we have 54 degrees of freedom. We haven't really talked a lot about degrees of freedom in this class, so at this point, when you see that, go ahead and just use the formula as you see it there. And it speaks to the type of t distribution that you're ultimately working with, or that the calculator is really working with behind the scenes. Okay, one more example here. Let's look at number 4. The Pew Research Center reported in 2008 that only 15% of 18 to 24-year-olds read a daily newspaper. The publisher of a local news wants to know whether the percentage of newspaper readers among students at a nearby large university differs from this percentage in general. She surveys a simple random sample of 200 students and finds that 40 of them, so 40 out of the 200, or 20%, read a newspaper each day. Can she conclude that the proportion of students who read a daily newspaper differs from 0.15? You see, we're doing a hypothesis test. As soon as you see that significance level, you know it's a hypothesis test. You look at that last question, and you know it involves proportions. This is not a means question anymore. So my hypotheses are going to look like this, where it's going to be p is equal to some number, and then p is going to differ from some number. But many times I look at that last question to gather what the alternate hypothesis is. And so if the researcher here is inquiring whether the proportion of students who read a daily newspaper differs from 0.15, then that's my alternate hypothesis. My null hypothesis is that there would be no change from 0.15. So we're doing a hypothesis test involving proportions. So we're going to say, let's go to one prop z test. And that is stat tests. And that one prop z test is number 5. P naught, that's the null value of our mean, or of our population proportion. We can see that that's equal to 0.15. X is the number of people out of the sample who satisfied a certain characteristic, which in this case is the number of people who are reading a newspaper daily. So that's going to be 40 out of 200. So this 20% that they give you in the problem is almost a misleading number in a way. 40 out of 200 is exactly what you want to be putting in there. And then you want to change that alternate hypothesis to be not equal, and then we can calculate. And when we calculate here, we get a test statistic of z is equal to 1.9803 to 4 decimal places, and a p-value of 0.0477, which, notice, that is really close to our significance level, but it is a little bit below. And so since that is less than the significance level, we will reject the null hypothesis. Remember, the p-value needs to be small. It needs to be lower than that significance threshold to reject the null. So this is another case where you would reject the null. And if you're rejecting the null, then that means you're accepting that the proportion, the percentage of students who read a daily newspaper does differ from 0.15. So I hope these examples help you, and now you could probably tackle the homework. Good luck.